Just, you know, it's like, yeah, a lot of lots. Yeah, they're not believe it out times. Yeah, so yeah, I don't know. I don't just being a blindfold or it's so weird. I don't like this word. Anyways, we saw when you used it, that's really interesting. So now there is more. They're getting golf course. Also known as and so I'm going to figure that out.
I know we got this working.
Actually, I'm still working on that. I'm gonna put a new mic in that.
Okay.
It's just not quite right.
Okay. And then the podium mic seems to be going through on Zoom, but not in the room.
1, 2.
I know, she like, it's like what you're in the business.
Yeah, that's a really quick reminder that you get shit.
Thank you all for walking over. We are having a couple difficulties with mics. The tech guy's helping us out here, so we're gonna get started in just a couple minutes.
Yeah. That works for us.
Yeah, it seems to be going, the mic is going to Zoom, but not to the room. I use pen teach. You okay getting started?
Yeah.
All right. Right. We are going to go ahead and get started. I'm going to warn everyone, we may have a brief interruption for some mic swaps. And then hopefully you'll all be in the room be able to hear better. But in the meantime, we will try to just project. And if you're in the back row and having a hard time, wave your hands or cup your ears and we'll speak up more. So thank you for being here. I'm Sarah Brewer. I direct our education program at Accords, and I want to welcome you all to today's education program seminar. What is Accords? Accords is our one-stop shop for pragmatic research. It's supported by the University of Colorado School of Medicine and Children's Hospital, Colorado. And it's an environment for faculty to conduct pragmatic research, receive various types of services and support for grants and projects, along with incredible mentorship training and education in health services research. So Accords conducts pragmatic research in real-world settings to improve healthcare and outcomes by providing a multidisciplinary collaborative research environment, strong methodological cores and programs like our biostatistics and analytic core, consultations and team building for grant proposals, mentorship training and support for junior faculty, and extensive educational offerings like this seminar series. All right, we can hear that. So before I introduce our
1, 2.
All right. Before I introduce our speaker and hand over the floor, I have a couple of housekeeping items about our seminars. The first is if you are virtual today, please use the chat throughout the seminar, share your questions, comments, and we will have time for moderated question and answer at the end of the talk. And then second, please complete an evaluation if you're here in the room. Those are backed by the sign-in sheets. And if you're online, you will see a link toward the end of the hour. So today, our seminar is part of our series, Statistical Methods for Pragmatic Research, and is the first of 9 talks in the series. Let me swap out here. Okay. And today, we welcome Dr. Katie Colborn. Dr. Colborn is an associate professor in the Division of Healthcare Policy and Research in the Department of Medicine. She directs the Biostatistics and Analytic Core at Accords, and she also holds a secondary appointment in the Department of Biostatistics and Informatics in the Colorado School of Public Health. She co-directs the Data Informatics and Statistics Core of the Palliative Care Research Cooperative Group. She has received extramural funding for her research and has collaborated on numerous extramural research grants. Her research interests include design and analysis of randomized control trials and cluster randomized trials, analysis of electronic health records data, and health services and outcomes research. Please join me in welcoming Dr. Katie Colborn today as she presents consideration for the design and analysis of pragmatic trials. Welcome, Dr. Colborn.
Hey. Thanks, Sarah. And thanks everyone for coming today. I think we have a pretty good turnout online as well as in person. I'm happy and excited to lead off this biostatistics education series that we'll be having over the next year by discussing things to consider when designing and analyzing pragmatic trials. So I'll begin with an overview of pragmatic research, and then I'll share some of my recommendations on how to best work with your statistician colleague on the design and analytic plan for a pragmatic trial. Next, I'll introduce several designs and discuss their trade-offs. And then I'll briefly introduce some common statistical methods for analyzing pragmatic trials. And then finally, just give you a little overview on the Accords Biostatistics and Analytics core. Okay, so starting with an overview of pragmatic research. I took a quote from my colleague at Accords who directs the Dissemination Implementation Core, Russ Glasgow. And in one of his publications on pragmatic trials, he defines pragmatic research or trials as designed to answer the question of whether a program works under usual conditions compared to explanatory trials that answer the question if an intervention works under ideal conditions. And some recommendations from that paper for the design of a pragmatic trial include research questions and outcomes should be important to stakeholders. These might include patients, policymakers, clinicians. The research is conducted in multiple real-world, often heterogeneous settings. There should be few exclusion criteria. So the participants are representative of those within the setting you're doing the study. And then comparison groups typically receive standard of care or some version of standard of care. From a second paper by the same author and his colleagues, Russ Glasgow, there are some recommendations on outcome measures for pragmatic research. This paper is called Pragmatic Measures, What They Are and Why We Need Them. I recommend reading this. This is a great paper. So from the perspective of the authors, important things include that the outcomes be low burden for participants in the study team to collect. They should be actionable. So there should be a immediate value to collecting that piece of information. They need to be important to stakeholders once again, and then they should be reliable and valid over time. So short reporting periods and ideally large effect sizes. And I agree with all of those points, and I'll add a few from the statistician's perspective, emphasizing again the large effect size being really important, low attrition. So make sure you're measuring something where you're not going to have a high risk of loss to follow-up. And then it should be proximal to the intervention. And I mean that in two ways. So first, to be close to the intervention on the causal pathway, and also to be close temporally. So that's again what Glasgow and colleagues pointed out about short reporting periods. And then choose something where confounding can be mitigated or isn't a really strong consideration. So quality improvement outcomes or process measures tend to be good outcomes because they can be easily measured and are more directly linked to the outcome. Whereas, quality of life or weight loss tend to be confounded with a number of other factors that might have nothing to do with your intervention and are harder to control. So your study is going to be powered on the primary outcome. So I recommend having only one primary outcome. Otherwise, reviewers might ask you to adjust for multiple comparisons. For secondary outcomes, you can have many, but you still might want to adjust for multiple comparisons on those. For pragmatic designs, it makes sense to think about how many of your measures are being collected outside of routine care, because the goal oftentimes is to disseminate or integrate into routine care. And so you don't want it to be a big burden beyond what's being done right now in clinic. If you're measuring a whole battery of patient-reported outcomes, for example, what's the likelihood that a busy clinic will adopt these surveys, and why should they? How will the information impact actions by the providers? So you want to think about these things when you're deciding what your primary and secondary outcomes are going to be. And I can think of few examples where a single time point is used in a pragmatic trial. This is because we're often implementing an intervention that needs to be evaluated prior to and after the intervention in both a treatment and a control group. So this comparison is often made using difference in differences, which you can see on the graph here on the right, an example of that. It's also referred to as a difference in slopes over time. How many time points you decide to collect is often a difficult decision. I tend to recommend 2 if the goal is to estimate a pre-test, post-test difference. More time points might not be linear, so it would require more tests of hypothesis, which could introduce type 1 error, or you would have to, again, adjust using multiple comparisons. So those are things to think about. If you are looking at a trajectory, that would be a good reason to collect more than 2 time points. And then another thing to think about is when you're designing your intervention, what is the stage of scientific maturity of your intervention? you're going to first decide what the outcomes are, and then you need to think about what's the intervention to impact those outcomes. And if it's well developed or not, or if you need to start back at the beginning and think about mechanisms. So I recommend looking at the NIH stage model. This is the stage of behavioral change model. And there's 6 stages, starting with basic science and ending with dissemination and implementation. Your intervention falls somewhere in these stages, depending on how it's been used in prior research, how someone else might have used it in prior research. And typically in pragmatic trials, we're somewhere between stages 3 and 5. Just a note on basic science. So in this context, it's not necessarily work in a lab, research in a lab. It might refer to a highly controlled environment. So often people studying behavior change in stage 0 are interested in the mechanisms or how the intervention actually works causally on the outcomes. And then after you've decided which stage you're in, then you can decide the setting and participants that might be involved in the trial. Finally, as far as the background on pragmatic trials goes, the last point I want to make is about choosing the right control group. This is important. It's typically either going to be standard of care or enhanced standard of care. Enhanced usual care provides a straightforward inference because you're actually controlling when the time points of data collection are, and you can align those with the intervention group. So if it's completely passive, it might be actually harder to get robust inference and results that are meaningful. These are ideally randomized at the individual participant level, treatment or control, but oftentimes that's not feasible or it's not relevant to the hypothesis. Randomization may need to be done in clusters, which I find to be the most common unit of randomization in pragmatic trials. And this is usually to avoid contamination or because you're intervening at a practice level or a clinic level. There's some interesting conversations in the world of statistics around staggered randomization, and a lot of that has to do with ethical considerations. So should everybody get the intervention and therefore we stagger implementation? Do we stagger implementation from a feasibility point of view? But I will caution people on that approach, and I'll talk a little bit more about that later. But it does complicate the implementation and also the statistical analysis if that's going to be your approach. And then finally, be careful of the Hawthorne effect. So if you think you're going to have a specific impact on your intervention, an effect size, consider a control group which isn't also going to have some improvement. So just being involved in a research study where you're collecting a lot of information kind of raises the awareness level of your control group, and sometimes they improve too. So that difference in differences needs to be even greater than you would think in just the effect size in the intervention group alone, because they might be, the control group might be improving as well. Okay, so now I'm going to talk a little about working effectively with a statistician to design, power, and analyze your research study. In my experience, this requires a phone or video conversation, not an email. It's not effective to have a first conversation about your study via email with your statistician. I think there's just too much to be discussed and too much that needs to be sort of taught between one another in that first conversation. So what to bring to your first meeting? Usually your specific aims page, doesn't have to be a final version, just a draft. A diagram of your study design and data collection schedule, as much as you have ready at that time. Primary and secondary outcomes. How are they going to be collected or measured? Are they surveys? What are the variable types? Are they categorical, counts, binary? And then a diagram of your conceptual model. And I'll talk more deeply about this because I think it's very helpful for facilitating that conversation. So your conceptual model is a graphical representation of the theories, beliefs, and assumptions in a research study. And it often shows the cause and effect relationships between dependent and independent variables, confounders, and other factors such as moderators and mediators. This is a version of a statistician's conceptual framework, and it's very general. It's a generic framework that you might use to communicate with an investigator about the research study. My colleagues and I at Duke University published this in a paper in the Journal of Pain and Symptom Management last year. And the boxes here represent constructs, each of which will be operationalized by one or more study variables. And the arrows represent causal or directional relationships. And the width of the arrows here indicates the strength of the relationship in question, the hypothesized strength anyway. So box B represents the factors which affect the strength of the intervention effect. These are often termed effect modifiers. So for example, if a pain coping intervention is more effective for patients with a primary diagnosis of cancer than for patients with other primary diagnoses, then we might use an interaction term here between the intervention and cancer diagnosis when we're estimating the effect on the outcome, the effect of the intervention on the outcome. Boxes D through F represent outcome variables arranged by location on the causal pathway. So the mechanistic outcome, which is box D, is directly caused by the intervention. So for example, if an intervention that focuses on pain coping techniques, you have an increased knowledge of pain coping techniques first, that's a mechanistic outcome. And then improved coping techniques might more directly affect a proximal outcome, such as maximum daily pain score, or a distal outcome like a patient-reported quality of life. So in this graph, this example here, we implicitly assume that the only way that the intervention affects distal outcomes is through the associated proximal outcome. But this is a simplifying assumption. And if, for example, a direct relationship between the intervention and quality of life exists, we could add an additional arrow there between those. Because the flow of causation not only can affect the relationship between A and D, it could also affect the relationship between A and E. We have a lot of options here that I haven't shown, but think of it as sort of a dynamic way to evolve that conversation between the PI and the statistician. The other assumption here that these arrows are making is that in each of these assessments of the outcomes, you would use the same covariates. Maybe each set of covariates would be different for the assessment of different outcomes. So you could have a different way of creating this graph, and this is often referred to as a directed acyclic graph, or DAG. So I'll just give you an example here. If we have a study with the following three aims, we can illustrate this process. This is a randomized trial of a pain coping intervention. On the left is the generic DAG for this study. Blue boxes are not used in aim 1. The green boxes and arrows represent the unadjusted analysis. So this extends from A to E. And the orange box arrow would be added to create the adjusted analysis. If you had an assumption that maybe some confounders need to be controlled for. And then in a RCT, oftentimes you don't need to control for confounders because that should be worked out in the randomization. But if it were a CRT, you might want to think about individual level confounders and a random effect. So the model might be different, but the way we might write out, starting with this graph and then moving on to sort of how would I write this out in a paragraph for somebody's grant application. Here's an example here. So aim 1 will be addressed using a t-test with study group as the binary predictor variable and daily pain score at 3 months as the continuous outcome. Recognizing that the t-test is a special case of a linear regression model with study group as its only predictor, this primary unadjusted analysis will be supplemented with a linear regression model with study group as the primary predictor and covariates included. And again, each aim should have its own statistical analysis plan, but this is just an example of how you go from the conceptual model to an analytic framework that you can work with and facilitate communication. Another example study, this is one that I supported that concluded last year. It was a multi-center randomized control trial of perioperative palliative care surrounding cancer surgery for patients and their family members, or periop PC. And I wanted to just provide a SAP template. So you might have a graphical SAP to begin with, but then your SAP template, as it evolves when the study is already completed and you're thinking about what are the primary papers that are going to come out of this study, it's good to have a SAP template for each paper. Our team tends to use it as if it's like a template for the paper. So what table shells are we going to be filling in? What figures you might want? And then I often ask either the PI or one of their residents or someone working on their study to literally map the variable names from the database to these hypotheses, because it saves time later on down the road. So getting everybody on the same page up front, I think, is a really efficient way to communicate. Okay, so another example of the graphical set for that study, and I just wanted to introduce this because sometimes things don't always go as planned. So for that study, because it was an RCT, we had randomized individuals to one or the other, the treatment and control group. And our hypothesis really was easy to test in that we had two groups and continuous variables, patient-reported outcomes, and we were essentially doing t-tests to compare those. However, intervention trial during a pandemic sometimes creates problems. So in the middle of the study during recruitment, we did have a pandemic surge in 2020. And so we kind of modified our analysis at the end. And this was actually something we did after many discussions with the PCORI Learning Network, which was a group that PCORI put together to help figure out how to analyze data after all of these curveballs were thrown at their studies during the pandemic. And many of us decided that a very simple, perhaps not the only solution, was to say, when was the peak of the surge, and then fit an interaction between the intervention and the pre-surge and post-surge, just to see if there were differences in outcomes by intervention group between those two periods. So this is how we modified it and just had to fit a slightly different model. Were we powered to detect that? Probably not, because we powered the study on no interaction. But either way, you could at least detect whether there was an effect, or at least if it looked like an inflection point graphically on that. Okay, so trial designs and trade-offs. I've already pointed this out a bit, and hopefully it's obvious to many people here who are very experienced researchers, but a randomized controlled trial is the ideal way to design your study. It yields the most power, it balances the confounders, and the statistical analysis is almost always very straightforward. It should be a t-test or a chi-square, unless you have some other complicated hypotheses around mediation. If there's a pre-post analysis, that can be thought of as a confounder, in that if you hypothesize that the baseline rate is different between the intervention and control group, you might want to calculate difference in differences instead of the distal time point difference only. Unfortunately, most of the time in pragmatic trials, we're not doing an RCT because it's hard to control. And we also want to look at how something works in the real world in multiple settings. So we're oftentimes looking at a cluster randomized trial. These are also very useful. The power is optimized with more smaller clusters compared to fewer larger clusters. Individual level data analysis, if that's the level of analysis you're going to be doing, you can include covariates, but you need to factor that into your power and sample size calculations at the beginning of the study. And the reason this is important is the concept of intercluster correlation. So this is a measure of relatedness of individuals within a cluster. When it's present, it reduces power because the observations cannot be thought of as independent, identically distributed. And that presents a problem when you're designing your study. So the ICC impacts the precision or power of your study through what's called the design effect. So in a CRT, you don't have independent observations, as I said, so you need to estimate what's called the effective sample size. So the equations presented here are used to estimate that effective sample size. And you can apply this to any type of study that you're doing. I often share this with investigators so that as they're thinking about their study, they can do this on the back of a napkin and think about how much it's going to be impacted if they change one or two factors like the number of clusters versus the number of individuals within a cluster. And you don't have to wait for your statistician colleague to get back to you with a new sample size over multiple emails. If you just play around with this equation, you can help yourself out a lot. So as an example to see how this works, let's say we want to recruit 360 patients into our study. We can enlist 3 sites, 120 patients from each site. And using the equations on the previous slide for 4 values of ICC, the effective sample size would be 360, 164, 107, or 15. So you can see if you have strong intercluster correlation, you have a very small sample size effectively at the end of the day. Now, if we instead recruited 36 patients from 10 sites, we would have an effective sample size quite a bit larger for each value of ICC. And the smallest we would have is 45. And I'll talk more about this, but you really don't want to do a cluster randomized trial with fewer than 10 sites if you can help it, because A, you need to actually effectively randomize those. And B, there are a few statistical models that provide robust inference with fewer than 10 clusters. So types of CRTs, there's the very standard parallel CRT. This is probably my favorite by far. It's straightforward. It's easy to get robust inference, but you do need to recruit at least 10 sites, which is often difficult. And this is, I show here 2 time points. So you could do a parallel trial where you have just 5 sites in a treatment arm and 5 sites in control arm and just compare those, but you don't really capture any temporal trends during that period that might have happened outside of your control. So it's always good to have that fully control set of sites to say, hey, if they went up a little bit, did at least the intervention arm go up more than what we saw in the control arm? Crossover, just like a individual level crossover design, these are used sometimes. They can be difficult to implement because sometimes you really can't go back from having learned something. So oftentimes these are educational interventions. And so if you're going into a clinic and educating clinicians, you're not going to be able to uneducate them. But there are situations where a crossover might be ideal. And actually, I published a paper with a student and John Kittleson a couple of years ago that showed that the crossover design yielded the most robust inference and the highest precision among a set of different approaches to analyzing cluster randomized trials. And then there's the step wedge. So this is like think of it as a staggered version of your parallel. I mean, you have a period where the clusters are not exposed to the intervention, and then you sort of stepwise introduce different clinics to the intervention. So the advantages proposed by the step wedge, or the creators of the step wedge, include that all participants receive the intervention. A staggered implementation could be more feasible for your study team. And they've often talked about increased power. However, these things are all possible with a parallel CRT. Okay, I'm exposing my bias here. But some of the disadvantages, which have been pointed out by Kotz and colleagues, which I encourage you to read these if you're a fan of step wedge, But the step wedge takes significantly longer to implement. It's therefore often a burden on the sites and the people who are implementing your study. And then the intervention is implemented in all clusters of the step wedge design, whereas it has not yet been proven to be effective. So I think if you're doing this and it's essentially an effectiveness trial, you should be careful to say that everybody should get the intervention, right? We should maybe show that it's effective before we plan on rolling it out to all the sites. I've also supported a couple of step wedge trials, and my impression is that the implementation is quite difficult, and that the power is not actually increased as much as you think it's going to be at the beginning. I've been a part of a couple failed step wedge, so that's my experience there. And another set of designs are adaptive designs. These are becoming more popular recently. Sequential multiple assignment randomized trial, or the SMART trial. One that's not as popular, but it's there's some interesting papers on it in the statistical literature, is the Learn as you go, or LEGO trial. And these are just dynamic treatment regimes. So you get randomized to a certain intervention, and then that might change throughout the study based on patient features. These are often used in HIV trials, for example, if you need to change a treatment regime mid-study. And I encourage you to read more about that. This, I'm supporting one right now with Dr. Sean O'Leary, where the goal is to increase vaccine uptake in a large number of pediatric practices. And that's also a cluster randomized trial. So statistical models. This could be an extensive talk, but I'm just going to focus on a few important tools that are used commonly in pragmatic trials. So conditional models, this first set of models that you're going to see most often are conditional models, and they include the well-known generalized linear mix models. These generally include one random effect. So if you're doing a cluster randomized trial, you would have a random effect for whatever your unit of randomization is. Some people make the mistake of adding one or two extra random effects, like maybe you have a site and some clinicians and patients nested within both of those. The traditional approach is to only include a random effect for your unit of randomization. So if it's the site, it should be the site. They're also useful for longitudinal data. So maybe you have repeated measures from the same patient. You should have a random effect at the patient level. And what's nice about these models is they're flexible enough to include more than one random effect, and that might be the unit of randomization plus repeated measures on the individual. The interpretation is a little funky, and nobody ever really interprets it the right way in their paper because it sounds funny, like for a given clinic, telehealth palliative care consults increase completion of an advanced care plan 25% more than in-person PC. So we usually don't say for a given clinic, but really technically they're conditional on the random effect. And so you should include that in your interpretation, but nobody's going to call you out if you don't. Again, I said it's best to have 10 clusters. There's some statistical methods for getting robust inference on a small number of clusters, but 10 really is ideally as many as you want. 8, I would say, is the minimum if you're going to do a GLMM, and then you might want to adjust your variance using methods that are out there for doing that adjustment. These are a good option for CRTs and longitudinal data, as I said, because they can allow for more than one random effect. Another set of models, semi-parametric theory, is marginal models. So these are used often in longitudinal data analysis. The trade-off is you can only include one random effect in a GEE. It requires a much larger number of clusters for robust inference. So I wouldn't recommend actually using a GEE if you're doing an analysis of a cluster randomized trial, unless there's a really large number of clusters. But if it's simply a longitudinal study from one site, and you have a bunch of individuals with repeated measures, this would be a really great approach. And it has a little easier interpretation, some marginal interpretation. So it's a population average effect of your intervention. So some notes on confounding. As I said, hopefully we don't have to adjust for confounders in the RCT. Some people, there's papers out there in the statistical literature that argue you should still adjust for confounders in a RCT. I tend to follow a more traditional approach of checking to see that balance was achieved in my randomization, and therefore I don't need to account for those in the analysis. CRTs, however, you often don't achieve that balance at the individual level. So you do want to consider any imbalanced confounders. You might look by treatment control after the study. Were they balanced on important confounders? If they're not, those might be confounders you consider including in a multiple regression model. But you need to think about those before you design your study. So list the 4 or 5 that you're going to check in your grant application, so that later you're not just doing post hoc analysis and committing type 1 errors. And the other piece of that is you need to make sure you've powered your study to include those confounders. And oftentimes people ask me, well, how do I know how many confounders? And I usually just say, I should be able to count them on one hand, hopefully, because I don't want a really nasty model at the end of a trial. The point of a trial is to really set it up well. So one way to handle that with a cluster randomized trial is to use what's called covariate constrained randomization. So we try to ensure that in our randomization process, some factors that we're able to measure at baseline prior to randomization at the cluster level are balanced across. So you'll simulate, hundreds or thousands of possible randomizations, and you'll only grab one from the set that meets a set of criterion on how well the confounders are balanced. And usually you only have a few confounders there, depends on how many clusters you have, but the fewer clusters, the fewer confounders you can really take into account when you're doing that type of randomization. And then other adjustments. So something you need to think about at the beginning of the study is, do I anticipate that not only is something going to be a confounder, but is it a modifier, an effect modifier? Or are there other factors that I really need to consider because it's important to some stakeholder out there, like social determinants of health is a big one. So what are those factors that you're going to collect, and how is that going to work into your analytic plan? Are they just going to be adjusted for in the analysis, or do you need to think about a stratified block randomization? So I've kind of shown a picture here on the right to represent perhaps that having a caregiver present at your visits would be an effect modifier, and you would want to ensure when you're randomizing your study that you end up with a balanced number of patients in your intervention and control arm that have caregivers. So that can be hard to do if you're not going to know who has a caregiver until they come and enroll in your study, right? So you might need to actually, instead of doing that at the randomization stage, just plan for that potentially being an interaction you have to test in the analysis phase. So think about what can be controlled or not controlled in the design, and what you need to power for in the analysis if it's not something that can really be controlled. So those are my, I guess, recommendations or considerations for when you're designing and analyzing pragmatic trials. We're going to have a great group of other statisticians coming to give talks on some of the more interesting details behind what I introduced. But then I also want to put a plug in for the Accords Biostatistics and Analytics core. We have 4 PhD biostatistician faculty, or at least part of 4 people, and 14 MS or PhD level data analysts. Our expertise includes mixed models, longitudinal data analysis, trial design, survival. We also have quite a bit of expertise now in machine learning and high dimensional data analysis. A lot of experience working with public databases and registries, and REDCap database development. We're also supporting a data coordinating center for a large phase large award for comparative effectiveness research. It's a PCORI trial with 20 sites across the country. And so if that's something you are considering doing, please reach out to us because we now have some infrastructure and some experience in handling that. And then, of course, we do pre-award grant development, and this is our link currently for reaching out to us for a consult. But otherwise, you're free to reach out to me, and this link is also on our Accord's Biostatistics website. And then here's just a list of the people we have coming, either hybrid or Zoom, for our future seminar series. So thank you very much.
We can fix that up then.
Okay.
Thank you so much, Katie. First, do we have any questions in the room? Yes, I know you all curious folks with lots of questions.
So we have a trial, pragmatic trial that only had 6 sites available. And due to constraints in the system, that was the maximum we could get. So we're pretty much stuck with the step wedge design from which is what we chose from what you just described. There's really no other attractive option available, right? Based on what.
That's right. You're gonna have to analyze what you have,
Yeah.
and that's fine. I mean, what is Fisher's quote of, you can perhaps do a postmortem evaluation of no, it's not that bad. It's really not that bad. And Hussey and Hughes would probably not like me right now for that, saying what I did, because they developed this methodology. If the implementation goes well, then you might have the benefit of repeated measures. So the reason you have increased power hypothetically or theoretically, is that you've taken repeated measures on those clusters. So you actually do have a pretty large sample size. If your hypothesized ICC was correct in the beginning, you should have pretty good precision. I think that the challenge is always, how are you going to analyze that? Because we often sort of say, okay, I need 10 clusters to do robust inference with a GLMM. If I don't have that, then how am I going to get robust inference? One thing you could do is, depending on what your outcome variable is, how it's measured, is to just analyze the clusters at the aggregate. So this is recommended by Hayes and Moulton and in their cluster randomized trial book, where you have essentially each cluster aggregated at each time point, and then you have those assigned intervention and control, and you're just doing a t-test between those. You don't have all your individual level data. You might not be powered quite for that. It depends on it, if it's a quantitative outcome or not, but I would say stay the course and it'll be fine. But if you're thinking about designing it in the future, get more sites. You randomize the sites, right?
Yes.
Yeah. Yeah.
Another question here.
I always, you just mentioned ICC, and this is one thing in trials that we've worked on in the past. I still I'm trying to get my head around, how do you estimate an ICC? I know when we do CRT design, oftentimes our statistician will encourage us, so let's look at several different ICCs. But is there a way to actually get a precise estimate that in the planning stage? So you just can have an ICC as opposed to here the ranges of ICCs. I mean, we saw what it did with the sample size and clusters, and you have different ones. And so it's it seems like a very important variable and a priori design of your trial, but I'm oftentimes kind of left with, I don't know how to actually estimate that.
Yeah, I think you have to hope to go back to the literature, but unfortunately it's often not reported in prior papers. People will say they fit a mixed model, and then there's no estimate of the sigma squared reported in the output, and there's no ICC reported either. So I would encourage people to publish your ICC so that other people can use it in estimation of, power for future trials. The other thing is pilot data are also not a good way to estimate either the effect size or ICC. And there's some recent papers on that too. If we had a panel of statisticians up here, we'd probably each give you a slightly different recommendation because we aren't entirely sure either. I believe Peter Diggle in the longitudinal data analysis book reports that on average, a repeated measures data set usually has about 0.02 correlation between repeated measures from the same person. Cluster correlation is tough. Sometimes it's really strong. Sometimes it's pretty weak. The values I gave are usually the full range of what I would try. I tend to arrive at about 0.01 because it has such a huge effect. And it's almost impossible to power a study that has a correlation of 0.2, you know, a cluster randomized trial. So when you're doing pragmatic research, you're going to have to think about like how heterogeneous are the clusters and are they too heterogeneous so that my intervention, I wouldn't be able to detect the effect no matter what I do. Or is there an environment where you could test it and the clusters might be a little bit more similar, or the patient demographic would be equally variable across those clusters, which would kind of diminish that cluster effect. I think you really have to consider the design and what your effect size might be. I'm sorry, that wasn't helpful at all, was it?
Still learning.
Yeah,
Katie, we have a couple questions on Zoom.
okay.
The first is, can you just share a couple of thoughts on optimization trials?
No, I can't. Yeah, I'm sorry, I can't.
That's okay.
Okay.
The second is, as statisticians, we understand the importance of RCTs. Do you have advice on how to respond to criticism of RCTs as not being patient-centered?
It's a good question. I guess I haven't done a lot of reading in that area. Probably because I usually want to do a t-test at the end of the day. But I think that it depends on what you're doing. I've done a lot of work with RCTs in palliative care and very extensive patient-reported outcome measures, which I think is very patient-centered. But I think that the issue with RCTs is that it can sometimes be hard to make the case that they're generalizable. So oftentimes they're within one site. And so is what you found in your one site generalizable to another population? Is it important to another population? And so it's probably easier to make that case if you're doing a multi-site sort of heterogeneous study, which was one of the recommendations of Russ Glasgow in his original paper. But yeah, it's a great question. I think it really depends on the context though.
What questions do we have here in the room? All the way around. I know you touched on control groups earlier and made myself a note. So I think we struggle with this a lot in clinical trials, what our control group needs to look like, which I think kind of goes to the question that you just answered. But I'm curious, like how you approach or maybe how your clinical teams have approached, like when standard of care is so variable, or when standard of care is no care, how you approach that in a clinical trial.
Yeah, that's probably a good question for somebody who's conducting the trial more so than me. But I will say that a lot of times no care at all isn't appealing to reviewers because it's too easy to beat, right? So people want to see, this is why comparative effectiveness research is so important, because you need to show that there's something out there that exists but what you're proposing is better than that. If there's nothing currently, it's probably not at the level of pragmatic trial. It's probably more at the mechanism phase, and you should first test that out in a very controlled environment to make sure whatever it is you're doing actually is efficacious. And then I would say that with having supported a number of studies in comparative effectiveness research, one of the issues with choosing the right control is that you have to choose outcomes that are going to be important to both groups, right? So you come in and you take a bunch of patient-reported outcomes on your intervention and control group where they haven't seen that at all in their clinic to begin with. It's almost impossible not to impact the control group, right? You're doing something that they would not do as a part of routine care. And so there's a trade-off between like nothing and too much. And that's what's hard about doing this type of work. The effect size has to be really huge. I don't know if that really answers your question, but that's my best statistical answer to your question, I guess.
We have time for one more question. Anybody in the room?
Yeah, yeah.
Yeah.
I'm gonna reach out to Frank.
Just in general, with the recommendations of 8 to 10 for those clusters, is that the same the designs where you have those that are purely controlled the whole time, or those that cross over? I'm not sure having them cross over or the stepwise design makes so you can have a fewer number of clusters.
Yeah, so it does help because you, it's similar to a longitudinal study in that way where you start with, if you have 100 patients, but you're going to measure them 5 times, you have essentially 500 measurements. And then from there, you can estimate your effective sample size, right? Because it's not 500 independent samples, but it's some fraction of that. That's where the benefit of the longitudinal cluster trials comes in too. You're taking repeated measures. So you essentially have a bunch more observations. And that's partly why I recommended the t-test, because you don't have 6, you have 6 times however many time points you have, and that's divided among your intervention and control, but it's not equal to that number exactly. So you'll want to actually estimate after your study what the ICC was, so that you can see how much was my overall sample size diminished by clustering. And one of the advantages of step wedge is that if you hypothesize really strong clustering, it's a good approach to take because you're going to need to take a lot of repeated measures. It's going to be a longer, more difficult study to implement, but you can increase power because if you literally can't get more than 6 sites, you're going to have to measure those sites multiple times to sort of get more samples to work with, if that makes sense.
Thank you so much, Katie. I'm gonna remind everyone to please do our evaluation if you are online. Jordan put it in the chat a few minutes ago. And if you're here in the room, those are back on the back table. And then I'm gonna do this. I'm just gonna share what some of Katie shared our upcoming stats series, biostatistics series, and then I just wanted to share some of our other upcoming offerings. So you'll see on November 1st, we have ethics challenges and messy decisions and shared decision making, which is our other series happening this year. And then I also want to point out that November 9th and 16th, we are about to send out our registration information for an overview of dissemination and implementation science workshops. This is a 2-day event with our D&I program faculty. So again, thank you so much for those of you online and for those of you here in the room. Have a great day.